last time, if you recall, we constructed a bunch of planes. And I wouldn't say that's an exhaustive way of, you could prescribe information in a whole bunch of different ways. And I could ask you to, find a plane through 2 points and not one or something like that. But, it's by no means an exhaustive list of data, provided, and then how to get planes from the provided data that we did last time. But I think it gives you a representative example of ways you could construct planes from certain pieces of information. So hopefully you could use those techniques in whatever comes up, and it'll help you out. So we found a way to construct planes given a whole bunch of different scenarios. We also looked at distances, right? So we found ways to calculate distance, and I should specify when I say distance, as it was pointed out in chat, I really mean the shortest distance. All right, so I'll use this interchangeably when it comes to distance between geometric sets or geometric shapes. So I found ways to calculate shortest distance between planes, between a point and a plane, and I think we also did a point and a line. So we left off with finding the distances between two lines that are skew, right? So now we look at finding the distance between skew lines in R3. All right, so let me just specify skew here means that this is non-parallel lines, and also they're not intersecting. All right, so here's the situation. We have a, let's say line 1, and then we have line 2 maybe passing underneath it in a sense. And we want to find the shortest distance between them, all right? So distance here between means the shortest distance. So how might we do this? So let's do a concrete example here. Suppose L1 is the line given to you by x of t, y of t, z of t is equal to, say 2 plus t minus 1, or let's say 2t minus 1 and 3t. And let's say L2 is the line x of t, y of t, z of t, which is equal to 1 plus t, 1 plus t, 3t minus 1, and minus 2t minus 1. What is the distance, which always means shortest distance between L1 and L2? All right, so how might we do this? Well, last time we said that one way to do this is, visually speaking, what you really want is you want to find a point on L1 such that it lies in a sense directly above L2, right? You want to find, they don't intersect, but there's at some point, you want to sort of find the vertical distance at the shortest. So there's some point where you could project where the lines, or the shadow of one line crosses the other in a sense, and the vertical distance is the shortest. But that's kind of hard to imagine in this scenario. So, well, what should we do? Well, one thing we saw last time was we saw how to find a plane that goes through one line and not the other, right? Especially if there's skew, that means that we could find the following situation. We could artificially construct a plane to, I think visually, I'm just going to alter this line a bit just so I could draw this out correctly. Or I don't actually know how to draw this out correctly. There's going to be some plane 2 such that it contains L2 and doesn't contain L1. And I'm going to be able to find a normal direction to this plane. And then what I could do is, if I have a normal direction, then whichever way I do my projection, I could choose a point on the second plane that I just artificially constructed, which is also on the line line 2. So I could do, let's say, point 2 on line 2, and then I choose any point P1. And if I draw the vector, say P2, P1, so the way I drew this, then the projection of this vector along the normal direction should be able to give me the distance, the shortest distance between L2 and L1. All right. So the construction is basically, once you find a normal vector to both of these lines, then by taking any vector point, from any point on line 2 and line 1, you could always project this vector into this mutually normal direction. And then this mutually normal direction has to be the shortest distance between these two lines. Yeah, apologies for not drawing this very clearly, but that's kind of the strategy here. Yeah, so P2 here contains L2, but not L1. And that's always possible from what we did last time, because well, because L1 and L2 don't intersect, right? And moreover, you could find a unique one because this is L2 and L1 are skew. That means that their direction vectors are different. So what you could do is, if I draw the direction vectors here, say here is direction v1 and here is direction v2, then I could set this to be equal to v1 cross v2, right? So the strategy here is set n2 to be equal to v1 cross v2, and then you want to take any displacement vector, say p2, p1, or p1, p2, doesn't matter, formed by points on L1 and L2 respectively. Then the distance is the absolute value of the component, or the scalar projection of the length of your displacement vector. So it's p2, p1 along your normal direction. All right, so we have a question from, does it mean make a projection of P2 on L1? Well, you can't really take P2 itself isn't really well, P2, the vector itself isn't the correct vector. You need to take a displacement vector from P2 to P1 or P2 from any other point, on L1. And you want to project it vertically, in the upwards direction here. So that's kind of the situation you want. So let's try and implement this in this case. In this example, let's say, what are V1 and V2? So remember, these are my L1 is given by this, and L2 is given by this. Someone should give me the direction vectors of V1, V2. It's possible. So V1 here should be a direction vector for L1. So here the coefficients of T are 1, 2, and 3. So this is 1, 2, 3. And then V2 here, the direction vector, read off the coefficients of T, that's 1, 3, minus 2. And so you could set n to be the cross product of this, and that's going to be minus 4 this way, minus, oh geez, these are bad numbers, huh? So this is minus 4 this way and minus 9 the other, so that's minus 13. Then you have 3 minus 2, it's 5. And then 3 minus 2, that's 1. And so I could choose any 2 points that I want, P1 and P2. And it's probably easiest if I just set T to be 0, right? So at T equals 0 on line 1, I could choose P1 to be 2 minus 1, 0. And then I could choose P2 to be equal to, at T equals 0, this would be 1 minus 1 minus 1. So P1, P2 or P2, P1 doesn't really matter. I'll go with P2, P1 because that's what I drew in the diagram. This is going to be 1 minus 2, that's minus 1. Minus 1 minus minus 1, that's 0, and then minus 1. Oh no, what am I doing here? P2 to P1 is what I want. I gave you P1, P2. Right, so I want the vector from P2 to P1, so that means take P1 and subtract off P2, so that's 2 minus 1, that's 1. 0, and 1 again. Okay, so here we are. So this means that the distance is equal to the absolute value of the projection, right? Now, what's a projection? That's 1, 0, 1 dotted with my unit vector in the normal direction. Now, my normal direction I got from the cross product here. So I need to take dot product of minus 13, 5, 1 with a magnitude. It's 13 squared plus 26 or something, right? So this is, let's simplify this a little bit. This is minus 13 up top. This is, so minus 13 plus 0 plus 1, right? So that's minus 12, but that's the absolute value, that's plus 12. So I could just get rid of this absolute value sign. And that's 12 over the square root of, 169, there you go. 169 plus 26. And you could add that up, that's 190, is that 190 something? That's 195, is that it? Square root 195, 12, okay. Maybe something like that. Okay, so that's your distance. Now let me address some of the questions I see in chat. Does it matter which way you subtract? No, it doesn't matter which way you subtract. One's going to be the opposite pointing vector than the other, but there's an absolute value sign, so it just destroys any sign issue that you have. Okay, so there's another situation here between, we found a distance between 2 skew lines, but there are other ways lines can be oriented, right? They're either, the distance could be 0 when they intersect. That's not very interesting. Now, they could also be non-zero but they don't necessarily have to be skew, right? In case two lines are parallel, you may also want to figure out the distance between them. So let me say distances between parallel lines that do not intersect, which just means they're not the same line. So in this situation, you have, let's say, L1 and L2. Let me call this L2. And I want to find the distance between them. All right, I'm going to draw this. And let's say I know vectors. All right, so I know direction vectors v1, and I know directions v2, and because they're parallel, they're in essence v1 is equal to some multiple of v2. All right, because they're parallel to each other. Okay. So in this situation, how might I find the distance between two parallel lines? So if you try to do so remember the technique earlier, and maybe this addresses Nimrat's question as well. The technique earlier that we sort of hid under the rug in this calculation was the fact that for two non-intersecting lines, we find a plane that is parallel to planes that are parallel to each other that contain each of these lines respectively, and we've calculated the distance between these two planes, right? If you have two parallel planes to each other that they don't intersect, the distance between them, the shortest one is always the one that makes 90 degrees between them. It's short. It's the shortest one by some trig you could do. So you want to find the vertical distances between these two parallel planes, and that gets you, in the case of skew lines, there are uniquely two planes that contain both of these respectively and are parallel to each other. You can find the distance between them, and the distance is exactly the distance between L1 and L2. Now, as we discussed last time, if you have two parallel lines, there is no longer a unique plane that is that are parallel to both of these. The point being, the previous method doesn't exactly work now. So in this case, how should we do it? Well, we could maybe move away from the plane construction and just look at the properties of the cross product again. So if I draw the following diagram here, let me do a point P1 and a point P2. I'm going to draw the arrow P2, P1, I guess is what this is. Then does this help me out anymore? Maybe I'll give you a little bonus here. So let's call this angle theta. If I know the length of this vector P2, P1, how might I express this line here in terms of this length and this angle, right? So remember by trig, right? This is a right angle triangle. If you draw a line down here, there's a right angle here. So the length of this is the length of this hypotenuse times sine of theta. Cosine of theta would get you the length here, which doesn't really do me any good here. So which vector operation gets me something times the sine of theta? Maybe think back to maybe a class or two classes ago. So I'm in the situation where I need, the length of some vector times sine of an angle it makes with another vector. So is that a dot product or a cross product? All right, so the dot product gets you cosine of theta. And well, I guess in technical terms, maybe you could turn cosine theta into sine theta, but it's easier to do the cross product. In this case, the cross product between two vectors is the magnitudes. The magnitude of the cross product is the magnitude of each of the vectors times sine of the angle between them. So visually, the distance is given to you by the length of P2, P1 times sine of the angle between them. Angle in this case being the angle this vector makes with V2, which is, V2 in this case is the same as V1. But what is this? This is the same thing. This is the same as the magnitude of the cross product given by the following. It's the cross product of P2, P1 cross the unit vector in the V2 direction, right? Well, in this case, V2 is the same direction as V1, so their unit vector is the same. It doesn't matter if you take V1 or V2. So this is going to be, it's a magnitude of the cross product here. And so the distance between parallel lines with direction vectors V is this, right? Oh, I guess I'll just do V here. It doesn't really matter which, they're parallel, so it doesn't matter which V you choose. Where P2, P1 are on the parallel lines, P2, P1. Oh no, L1, L2, L1, sorry, respectively. So I won't go through an actual example here because we're running short on time. But if you want to practice with the actual, an actual situation, I'm sure your textbook has some problems for distances between parallel lines. The reason you use a cross product is this is the quantity you want, and to get this quantity, it's the same thing as the magnitude of this vector times the unit vector here, right? The magnitude of this cross product is this times the unit vector length, which is 1 times sine theta of the angle between them. There's not really a way you could find the angle between them unless you use you could use the dot product first. You could dot this vector with this vector and find the angle in a sense by the dot, by using cosine theta equals, etc., the dot product over the magnitudes. And then you could just do the length of this times the sine of this angle, but that's probably as many steps as doing this directly. Because I'm getting a lot of questions on this. Remember, the magnitude of V cross W is the same thing as V times W times sine of the angle between them. Okay, well, so this is instated. It's for R3 in a sense because you're using the cross product. But how would you adapt this for two parallel lines in R2? Well, in R2, you could pretend both of these lines lie on the same plane, right? In this case, it lies in the R2, the sheet of paper or this screen that you're looking at. And you could just append a coordinate at the end. P1, if P1 were if this line were x of t, y of t, then this line in 3 dimensions, you could write it as x of t, y of t, z of t is always equal to 0. The same thing here, and you could look at this, you could pretend the situations in R3 and apply the same formula, right? Just contain these in the same plane, which are in R2, and pretend R2 is actually the xy plane in 3 dimensions. And then that will give you a valid excuse to use this cross product, right? Otherwise, you can't do the cross product in just 2 variables. Okay, let me move on to something slightly different. We found ways now of finding distances between lines now, and we found, that sort of completes our survey of how to find distances between straight line-looking objects, right? We found planes in a sense that are very flat and linear, and and lines which are also one-dimensional, linear sort of shapes. Now, one thing we didn't address was how to figure out if lines intersect or not, right? Here we have, in essence, we found ways to find distances when distances are not necessarily 0. So how do we know when distances are 0 between 2 lines? In other words, how do we know when 2 lines in R3 are intersecting? So let's take a look at this. Let's do lines L1 given to you by, let's just do x, y, z is equal to 1 plus 2t, 5 minus t, 3t, and 4 minus t, 2 plus t, and 6 minus 2t. Do the lines intersect? So how might we solve this problem? It is a system of equations. And let's say if so, where? So what does it mean for the lines to intersect? Well, it needs to occupy the same x, y, and z coordinates, right? At some point, at some time. So how do I set this? Well, they intersect if there is a point x, y, z is on L1 and L2 both. So let's look at the x equations. So the equations, in x, this means on the one hand, you need to have some time where x is equal to 1 plus 2t to be on L1. And what should I set on the right-hand side here? 1 plus 2t must be what? Right, so intersecting here means a slightly different thing than colliding, right? I'm not asking if you have a particle moving according to this and a particle moving according to this, whether their trajectories collide. That means at the exact same time, they reach the same point, x, y, z. But it's very possible for 2 lines, right, the image of 2 lines in 3-dimensional space to have trajectories that cross each other, that intersect. But they don't necessarily have to reach x, y, z at the same time. So how do I account for this? Well, I should actually write this in terms of, let's call this 1 plus 2t1 must be equal to 4 minus t2. All right, where t2 is a separate parameter now for L2 and L1 is is parameterized now by T1, because I'm looking at whether the images here collide, cross each other, not whether the actual paths themselves collide. So for example, this were L1 and this were L2, they can't intersect but reach this point at different times. So I need to account for this possibility by introducing a separate time variable for L2, because in essence, the clock in L1 and the clock in L2 are in slightly, they don't have to be synchronized in a sense for me to answer this question. I'm just looking at the images of the paths they trace out. So in Y now, I'm looking at the equation 5 minus T1 is equal to 2 plus T2. And in Z, I'm looking at the equation 3T1 is equal to 6 minus T2. All right, so let's take a look at this system. So this Y equation, I could simplify down in the following. If there are T1 and T2, that's how I did this. I could rearrange this by moving things around a bit. This is the same thing as T2 must be equal to 3 minus T1. And using this fact, I could plug that into any equation I want here. Maybe I'll use this to substitute into here to eliminate T2. So this now reads 1 minus 2T1 is equal to 4 minus 3 minus T1, right? And what does this get you? This gets you 1 minus T1 is equal to 3 plus, that's not 3, that's 1. Sorry, 1 plus T1, which gets you what? Well, T1 has to be equal to 0. So T1 is equal to 0 would mean that here, if T1 is 0, then T2 is equal to 3. So what we have so far is T1 is equal to 0 and T2 is equal to 3. Solve the equations in X and Y. Now, what does it remain to check? So question here is, I now have solutions T1 and T2 for these separate clocks that L1 and L2 are running on, where they share the same X and Y variables. What else do I need to check? So, I verify the points are equal at those times, right? So I've definitely checked, because I've solved using these first two equations, I've solved for T1 and T2 such that they definitely share the same X and Y variables, all right? So I now need to verify, do they also share the Z variable at this time? So 3T2 is going to be equal to, 3T1 rather. So on the left-hand side of the Z equation is 3T1. And now T1 is equal to 0, then this is equal to 0. And 6 minus 2T2 is going to be equal to 6 minus 2 times 3, which is 6. And these are equal to each other, right? So this is fine. So in this case, they do collide, or no, sorry, I shouldn't say collide, they intersect. Precisely, you don't know if they collide or not, but they do intersect at point at T1 is equal to 0. So now you could plug in either T1 equals 0 or T2 equals 3 to any of these equations respectively. Well, at T1 is equal to 0. Let's look at L1. So this is at 1, 5, and 0. All right, so questions, let's see. Why did you substitute 3 minus T1 for T2? Well, because I need to figure out a way to solve this system. Right now, if you're taking some linear algebra, remember something about systems of equations. Here you have 3 equations and 2 unknowns. T1, T2 are your unknowns, and you have 3 equations here. Now, unlike our previous example, which was to do with dot products, we had an underdetermined system. That means that you had possibly more than one solution. In this case, you have more equations than unknowns. This means you have an overdetermined system. There might be no solutions at all. But what you do in this situation is you forget completely one of these equations down here. You remove one, any one you want, and now you solve a system first of 2 unknowns and a system of 2 equations with 2 unknowns. That should be formally solvable in the sense that you have the same number of unknowns as in equations. So you try and solve that first, right? Because if you can't even solve that, then you're in big trouble. So you solve this first, and that's why we substituted in t2 equals 3 minus t1, because this simplifies down. You could solve this out, and you could now, just for these two equations, you solve for t1 and t2. And then this is overdetermined, so now you have to plug your candidate t1 and t2 in that solves the first two equations and see if it also satisfies the third. If it does, then you intersect. If it doesn't, then you're doomed and it doesn't intersect. It does not. All right, so let's do a bonus follow-up. Let's say if particle A traverses L1 with parameterization, and particle B traverses L2 with second parameterization, do these particles collide? So when you're asking whether particle A and particle B collide, the clocks do matter now. In a sense, at every single given joint clock time, you have a start watch according to t, and at each particular t, you know exactly the point at which particle A is and what particle B is. And for them to collide, it means they have to occupy the same point at exactly the same time t. So in this case, do they collide? So one thing you could think is, well, we did a lot of work here, right? We certainly know where the paths intersect. Now, certainly, if they collide, then it would have to be at one of these intersection points, right? It, in fact, happens at an intersection point where the times are exactly the same. It's not possible for you to collide at a point and not intersect at that point, right? Because if you collide at the same point, that's actually, you satisfy a stronger condition there. You arrived at the same point at the same time. And so if you collide at a point, you certainly have to intersect at that point because you must be at the same place, right? So we really just have to test out whether the intersection points are a collision point. There's precisely one intersection point. Later on, when you have more general curves, there might be more, but in two lines, they could intersect at most one point. So there's one point here where they intersect, 150. And the question becomes, do A and B arrive at 150 at the same time? And in this case, what's the answer? They don't, because here, for particle A traverses according to this path here. At time equals 0, particle A is at 150. Whereas for particle B, according to this parameterization, well, we saw particle B arrives at 150 at time equals 3. So they do not. So particle A arrives at 150 at t equals 0. Particle B at 150 at t is equal to 3. All right, so that's a little bit on the intersection of lines. And now, so where is the line? X, Y, Z is equal to 3t, 1 plus 2t, 2 minus t, intersect the plane 2x plus 3y minus z, 4. And here's a slightly, maybe if that one's too straightforward for you, it's nice to think about, but here's a slightly different one, which also segues into what we're going to do next, which is cross sections. All right. What is the intersection of the plane 3y plus z is equal to 0 with the sphere x squared plus y squared plus z squared is equal to 4? All right, maybe we'll continue with seeing your suggestions for how I might attack these examples. So in this case, how should I, what's the strategy here? I have a line with, it's parameterized, in this case, by this parameterization here. And I'm asking when it intersects, or where it intersects a plane. So what should I plug in this case? Well, the strategy here is to plug in parameters to the plane equation, solve for t, and read off the coordinates x, y, z at t. just because we're short on time, I'll actually leave this for you to do as an exercise on your own. By the way, if I didn't tell you that this line intersected the plane, how might you determine if this line intersects the plane or not? What might be a quick way of figuring out if this line intersects the plane? So one thing we note is that if you have a line that is perpendicular to a plane, maybe I'll ask a question. In what scenario does a line not intersect a plane? Is it when the line is perpendicular to it? Is it when the line is skew? Or is it when it makes a different angle to the plane? Or is it when it's parallel to the plane? Right, so how might I determine if this line is parallel to the plane or not? Just read from the way I've presented it in this problem. I know the equation of a plane and I know the parameters for this line. What determines if the plane and line are parallel? Right, so I could immediately look at the normal to the plane, which is 2, 3, 1, or 2, 3, minus 1. And I could evaluate the dot product of that with the direction vector, which is 3, 2, minus 1. And if the dot product of the normal vector to the plane and the velocity vector of the line, if the dot product is 0, then certainly they make right angles to each other, which means the line and the plane are parallel, which means the line will not intersect the plane unless it lies on the plane, right? So you could quickly do a check using that to determine whether a line or a plane intersects. As long as the dot product is not 0, then it will intersect. And so you could very quickly decide whether the intersection is even possible. And once you figure out if the intersection is possible, then by plugging these equations in, so substitute x with 3t, y with 1 plus 2t, z with 2 minus t, you solve for t, right? It's a single equation. It's a linear equation in t, so it's not too bad to solve. Okay, so how might I do the second example here? Well, I could substitute in 3 plus z is equal to 0, which means z is equal to minus 3y. And so x squared plus y squared plus z squared is equal to 4. That becomes x squared plus y squared plus, well, z squared is now minus 3y. So this becomes 9y squared is equal to 4. So this means that x squared plus y squared, x squared plus 10y squared is equal to 4. And now this is kind of a stretched out circle, right? If I now plot this, in a sense, what we're doing here is I have a sphere and I've sliced this by a certain plane here. I sliced it off with a plane. And now if I look at this plane and just put x and y directions on this, then what I have here is something that looks like a squashed circle, right? This tells me this sort of intersection is described by, if I set y is equal to 0, then the x intercepts are at minus 2 and 2, right? Because you want x to equal 4. And the y intercepts are, when x is equal to 0, you want y squared to be equal to 4 over 10. So that's 2 over root 10. This is not to scale, clearly. And so what you have here is a cross section that looks like this. All right, so that's this intersection here, or this intersection here. Does this make sense? This is, as we're solving, you basically have two equations now, and you want to solve algebraically for what the intersection is. And the intersection, visually, it looks like this. You have a plane here. You're looking at the set of points x, y, z that satisfy this plane equation, which I've drawn schematically in turquoise as a plane. And you have a sphere here of radius 2. All right. So instead of doing this, what we're going to do next is we're going to look at these classes of surfaces called quadrics, and also some cylinders. In general, this is how you find intersections of planes with spheres. And next, we're going to look at something called cross sections, which are very special intersections of surfaces with planes that are parallel to the coordinate planes. All right, so these are intersections of surfaces S with planes parallel to coordinate planes X. These are the XZ planes, the YZ plane, and the XY plane. And what this means visually is take a sphere, S is equal to, let's say, x squared plus y squared plus z squared is equal to 4. The z is equal to k trace, or cross section, is x squared plus y squared plus k squared is equal to 4. In other words, this is x squared plus y squared is equal to 4 minus k squared for constant k. And what this gets you is you have a sphere, and you're intersecting these by planes z is equal to k. All right, so this plane is parallel to the xy plane. And what this gets you are circles. Now, x squared plus y squared is equal to 4 minus k squared. So at z is equal to k, the intersection is described by a circle of radius root 4 minus k squared. All right, so here in my really bad example, you've been slicing things by planes that are not necessarily parallel to the coordinate planes. And that, in a sense, it doesn't really distort well, right? It gets distorted when you look at it parallel to xy or yz, for example. So it doesn't really give you a nice representation, if you would say, of your surface. But if I instead just fix a family of planes given by z is equal to k, where k is a constant, well, at z equals 0, I get the intersection to be a circle of radius 2, right, when this is 0. At z is equal to 1, I get a cross-section or a trace that looks like a circle of radius root 3. And all the way up to k is equal to 2. At k is equal to 2, I get x squared plus y squared equals 0, right? So it shrink down to a point because x and y have to be 0. And in that sense, I could slice up my surface by different, in a sense, by a plane that's moving upwards. And I could see at how the cross sections fit together, and that could build me a surface together, right? So in this sense, the z equals k cross sections, or your text would call them traces sometimes, are circles of radius root 4 minus k squared. Similarly, you could also have the same situation here as before, and you could slice this with planes that are parallel to a different axis. So for example, in this case, this is a plane which is given to you by y is equal to k. And similarly, you have x squared plus k squared plus z squared is equal to 4. So this means that your cross sections are also circles of radius 4 minus k squared. So this means that your y equals k cross sections, circles of radius 4 minus k squared as well. And right, so when k is greater than 2, you get no circles whatsoever, which makes sense, right? This is telling you that if I slice up my, I have a big trouble with surfaces in 3 dimensions. I mean, they're hard to visualize in a sense. So what you could do is imagine you're slicing up all of R3, your 3-dimensional space, by planes, right? In this case, you're slicing it up with horizontal planes that are moving from k equals minus infinity to k equals plus infinity. And when you're way down at k equals close to minus infinity, well, there's no intersection whatsoever with your shape, in this case, a sphere. So when k is less than minus 2 in this case, there's absolutely no intersection. And then as soon as it hits 2, you start seeing a slice, right? There's a little slice as a point. And then as you move, as you move your plane upwards, in this first example here, you move it upwards, you're going to see circles are growing until it gets radius 2 circle at z equals 0, and then they're going to shrink again until it vanishes again. And in that sense, you could get a good sense of what this shape is just by looking at what the cross sections are. Now, things are a bit more complicated when you look at a bit more, varied shapes. So let's look at the following. So consider the shape, the surface, y is equal to x squared in R3. What are the x equals k, y equals k, z equals k traces or cross sections? So in this case, note that there's absolutely there's no restriction on z here, right? So in R3, you're just looking at the set of points x, y, and z, where y is equal to x squared. And when there is an elimination of one variable, when one variable completely does not appear, these are sometimes called cylinders. They're not cylinders in the traditional sense of a circular cylinder, but in a sense, they're formed by the translation of this curve. Y is equal to x squared is a parabola in the xy plane. And basically, you could drag this parabola in the z direction. And, that the swept out shape is what the surface is, because there's absolutely no regard to what your z value is here. So at every single z slice, you look like a parabola. So we could try this, right? We could view this as for z equals k, y is equal to x squared. So this means that when I project downwards on the xy plane, the shadow of this shape is always going to be a parabola. Let's see, projected to the xy plane, the z equals k cross section is always going to be this parabola. Well, it's a standard one. Looks like this, right? And then you could also look at what the y is equal to k cross sections are. When y is equal to k, well, this means that x squared must be equal to k, which means that x, well, one way we could say this is x is equal, when k is negative, you get absolutely nothing, right? There are no solutions, no real solutions to x squared equals something minus something negative. As soon as k is non-negative, then you get pairs of solutions, right? X is equal to plus or minus root k. And z is completely free to move, right? Z is between minus infinity and infinity, because there's absolutely no restriction on what z is to satisfy this equation here. So what you have is on the zy plane, or projected the xz plane, you have the following. You have x and z here. And for every fixed k, let's say if k is greater than 0, you have minus root k plus root k, and you have these vertical lines here, right? Where x must be equal to minus root k or plus root k, and z, there's absolutely no restriction in what z is. All right, so let me try and put these two cross sections together and answer your question, what this looks like in R3. So together, what this looks like is you have a circle, or sorry, a parabola. Let's say on the z equals 0 slice, that's the xy plane. You have your parabola that looks like this, right? That's this. That's from this slice here when z is equal to 0. And then as you move up, this doesn't change, right? I guess send this out. You can move up here. And on this slice, this is the z equals, let's say, 1 slice. It also doesn't change, right? For every single k, your projection always looks like, when you look down from above and look at what this is on the along the xy, its shadow in the sense of the xy plane. You look down from above, it always looks like a parabola. And so you could build up for each slice, it looks like this vertically. And what happens when you slice it the other direction? Well, the other direction you could look at is I've built out the y equals k slices. So let's say when y is equal to 1, I could have a vertical plane here that's given to you by y is equal to 1. And how does this purple vertical plane y is equal to 1 intersect with my shape y is equal to x squared? Well, I look at its traces, and its traces are exactly, it's going to intersect somewhere here and maybe somewhere here. And these are exactly at minus root k and plus root k, or sorry, minus root k and plus root k. And there's going to be a minus root k somewhere here. And as I slice y is equal to 2, y is equal to 3, as I go further this way, these lines are getting further apart, right? As if I look at how this orange surface is, when I intersect it by these purple planes that are moving this direction, I'm going to get two lines that are moving further and further apart. When y is equal to 0, I just get the central axis here. When y is equal to something negative, there are absolutely no solutions to this, right? And I also see absolutely no intersection between this orange surface and this purple curve here, right? So the surface here looks something like this, right? That's kind of how this looks like here. It extends, infinitely upwards and downwards, but this is roughly what the surface looks like. So this is called a parabolic cylinder. All right, and in general, cylinders are, once again, so they're given by algebraic equations like this in R3, where you're missing one of the variables. There's only a relation between two of the variables in R3. And whenever that happens, you basically look at the two variables and look at its shadow in these two variables. In this case, it's a y equals x squared. It's a parabola. It's a somewhat easy shape for us to remember. And then you just drag it in the missing variable. And in this case, the missing variable z, you just drag it up along z, and then the region it sweeps out is what we call a parabolic cylinder. A circular cylinder, the one that we're used to, is one where it's x squared plus y squared, for example. Or let's say x squared plus z squared equals 1. Right? That would be a unit circle in the xz plane. But because we're in 3 dimensions, there's no restriction on y, so you could just drag this circle up and down y, and you get a cylinder that's circular in the y direction. So yeah, the intersection for, if you fix z is equal to k, or sorry, y is equal to k in this case, the intersection is just 2 lines, right? If I take this shape here and I slice it this way, right, in purple, if you look at this and I slice it this way, then there's only 2, for every y is equal to constant, there's going to be 2 lines. There's a vertical line here and a vertical line here. So that's why there's 2 lines here in the shadow. K is any constant. So in this case, k is equal to 1. You can make a k is equal to 2 and all that. Oftentimes in the WebAssign and things like that, you see surfaces given to you by, x equal k, y equal k, z equals k, where k is a constant, but eventually you want k to vary, right? I could also ask you, what is the x equals 1? What is the y equal 1 cross section? And the y equals 1 cross section, that's x squared equals 1. So your solution here would be minus 1 and 1. And that's exactly what this slice is. This is a y equals 1 cross section. All right. But in general, because cross sections for the shapes we look at are somewhat nice, you could vary k to get a nice, what you really want to do is vary k iteratively, in small increments to slice out the surface, right? And to figure out what the surface does, right? Like that's probably how a way to generate computer graphics, right? If you should program something to try and graph out something, some 3-dimensional shape, then you would set one of the parameters, maybe y is equal to some constant k, and then just look at what your surface looks like across each of these slices, and then glue all these slices together to form your final 3-dimensional shape. All right, so I actually only drew 2 of these and worked these out. We're missing one of these, so x equals k I didn't do, so try on your own. All right, it should be very similar to this, but in each cross section you actually only get 1 line, is what happens here. Okay, I know this is a bit rushed at the end, but we got to get through this. Let's try the following. What are the let's say y is equal to k, and let's say z is equal to k traces. Well, actually, let's do something slightly different. This is here's where I get burned, but let's do y is equal to x squared. So let's do, for y is equal to k, what does this get me? This gets me k is equal to x squared plus z squared. So for positive k, what is this? Or for for positive k, what is this? What are these shadows? X squared plus z squared is equal to k. Right, these are circles, and when k is negative, they're nothing, right? So when k is positive, this is going to be a circle of radius root k in a plane that's parallel to xz, right? And now, what happens when z is equal to k? Well, I get something that looks like y is equal to x squared plus k squared. And remember, k is a constant, so pretend k is 1, for example, then you get that the cross section, or the trace at z is equal to 1, is y is equal to x squared plus 1. And what is that? What's y is equal to x squared plus 1 on the plane? Yeah, well, not a cylinder quite yet. Remember, the traces are curves. So this is quite honestly just a parabola, but translated, so it's close. This is a parabola that's translated by k squared, right? This is the parabola y is equal to k squared. And this is kind of symmetric, right? You could do the same thing for, if I ask for the x trace, it's the same thing. For x equals k, you just get y is equal to k squared plus z squared. So you get if you put y and z here, or sorry, if you put y and z here, then you get also a similar parabola for the k trace. So I didn't ask for that one. How does this fit together? This fits together like the following. So y is equal to k, these are circular slices. And if you slice, let's say z is equal to 0, at z is equal to 0, so that's the xy plane when I set k equals 0, you get the parabola y is equal to x squared, right? So you get parabola is equal to x, something that looks like this. That's horrible. This is a slice at z is equal to 0. And then as you slice z is equal to 1, you get a parabola that looks like the same thing, but it's instead of having a vertex here, it's moving slightly here. And so for purposes of drawing, it's probably easier to draw the y trace now. So at y is equal to 0, that's not very interesting on the xz plane. Y equals 0, this is just a point here. If I put y is equal to 1, say, if y is equal to 1, then you have a cross section of a unit circle. And as y increases in k, you get a circle of larger and larger radius. And so what you end up getting is you get a shape that looks something like this, right? Opening up in the y direction here, right? It is this shape here. For every y slice, it's a circle that grows. And so this is called a paraboloid. And the trace will always give you a two-dimensional image in the sense that when you're taking the trace, you're taking away one of the variables, right? At z equals k, it's literally a plane. So you're looking at how the plane slices your two-dimensional object. So it slices it along a curve. So when you picture what a trace is or a cross-section is, it's always going to give you a curve that you could represent in a two-dimensional space like this. All right. Now, when you slice this upwards, I'm not going to draw it because then I will actually ruin everything. You see that if I go up here at z equals 1, I'm going to get, I'm going to slice this horizontally, and I'm going to get another parabola, but it's going to not go, not going to end up here. It's going to end up maybe here, and so forth, right? I'm going to slice this horizontally, and I'm going to get parabolas running this way. All right, so in this case, if you look at the Weber sign, oftentimes you'll see many curves in a trace. And let's say y equals k, the y traces, for example, the y traces are going to be circles. They have a lot of circles that are concentric to each other. And what that means is they're basically, they're letting k vary, and they're taking all the projections of k onto the xz plane, because you could do that. And you're looking at how the shadows vary, and they label each of these k. So that's really the only difference in maybe style that the textbook would present to you. It tells you it would draw out each one of these and put them all in the same plane, and you'll see growing circles, all right, as the growing shadows of this. It doesn't really, for practical reasons, it doesn't really matter what these things are. Right, so the other ones to study, maybe should try the traces for x over 4 plus y squared minus z squared over 4 is equal to 1. And by trying the traces for is just, set each of these variables to k, or a constant like 1 or 2, and see what the cross sections are. And this turns out to look something like a shape that looks like this. And if you look at this means setting z equals constant on these slices, you get circles, or I guess sort of ellipses in this case. It's x squared over 4 plus y squared is equal to 1 for z equals 0. So these are ellipses. And if you slice this vertically, in a sense, when let's say when y is equal to 0, you get x squared over 4 minus z squared over 4 equal 1. So these are hyperbolas. All right, so these are hyperboloids of one sheet. And sorry guys for the rushed ending, but thanks guys.